Okay, hello everyone. So my name is Akshay Shankar, and today I am going to explain about the inversion algorithms for scientific ambient noise source imaging. And first up, I start with get simplified. Start simply with a simple model. So basically, this is source inversion using a homogeneous velocity model, and then I move to a non-homogeneous velocity model. So to get started, we have a domain of 50 km by 50 km, starting from minus 25 km to 25 km. There are sources placed along and receivers as depicted by the diamonds in the figure. So the sources can have different intensities, and in the homogeneous velocity, you have a constant speed of 2 km per second. So basically, from that source distribution, the true source distribution, I compute the cross correlations, which are talking about the similarities between the two signals sent by two different receivers. So hence, since this takes us a lot of time, I have done only for 20 and 50 receivers. So if you want to do for more receivers, you will need something which is known as supercomputing. And yeah, because of the lot of permutations and combinations that you have with the receivers. So basically, once this is done, this cross correlations are computed for these permutations, it's time to perform inversion and get this model using a set of iterations. So in that iterations, the misfit keeps decreasing, and at one point it remains constant. And once it remains constant, it will increase. Hence, the loop is terminated at that point. It remains a constant. The misfit is a constant. So there are two algorithms. They are gradient based. One is the Gauss-Newton method, and the other is LBFGS, which uses a limited amount of memory. Now, coming to the non-homogeneous model, the velocity is not uniform everywhere. So there is a perturbation given, and that perturbation results in a Gaussian. As you can see, it looks like a checkerboard. But the only difference is, when you are doing inversion, the inversion is calculated here using either a homogeneous model here or a non-homogeneous model, as given in the figure. So this inversion is performed using a non-homogeneous model, and this inversion is performed using a homogeneous model. And in both cases, the data is calculated using the non-homogeneous velocity model. And another big question is, where can you apply this? So you can apply this in tropical cyclones, where you can study how it is moving, how it is progressing, and how much it is dissipating, how much energy the cyclone is dissipating when the cyclone hits the land. Another application is studying about sediment transport. So this sediment transport, these models can give you an idea of the flux of your sediment. Basically, how fast it is moving or how slow it is moving. And another thing I would like to mention is regarding the power spectral density. So that flux of the sediment, that is got to do with power spectral density. So that power spectral density is dependent on the momentum of your particles and the number of particles. So that result, in that you can apply it to restoration of rivers and how mitigating your floods, eradicating floods. So everything is done at the river bed. Thank you.